Do you have video? I don't see, got it there. The problem with, I don't see any of this in the other screen, so I have to escape it.
Yeah, escape.
No, escape doesn't work either.
Oh.
I have to go to this. I'm actually.
Try, yeah.
Yeah. If you look at the screen, if you look at the
Where is the projector?
No, the screen.
Oh, I have to look at the screen and do it because I don't. There we go. Okay, so let's start from here. Okay, so sorry for that. My name is Hae-Young and I'm from Toronto, and I'll be talking about the Kitaev interaction, and I have to do one more, got it. Where is my, there you go. Okay, and I'll talk about the Kitaev interaction and Kitaev materials. Okay, so let me begin with thanking my collaborators. This has been quite a while have been working on this. So over the 10 years or more, I've been kind of lucky to working with many people listed here. And yeah, it mainly consists of my groups of formal student and formal postdocs, and the current student and current postdocs. And in addition to the people at U of T, I also had extensive collaborations with people outside the U of T involving numerical person Eric Sorensen and Ian Affleck at UBC, and Yongbak Kim, as well as the Simon Travis at Germany, and Matthias. And those are the one of the long-term collaborators. Experimental collaborators has been playing an important role here, and most important one would be Young Kim, who has been working with me along the line of this ruthenium trichloride, as well as the Ken Butch. I'm currently working with Louis Yang at Tsinghua University about this pump probe experiment. So I was really curious to learn more from Eugene from the last talk. And Hide Takagi, as well as Embryo So, has been not working on the honeycomb in particular, but we've been working on the perovskite iridate, and that has been a kind of building block for this honeycomb materials. So I thank for these two collaborators as well. And I also like to special thanks to the Guineat because along this line of the my studies, he's been always encouraging and having given me a lot of inputs on the intuition to this material issues. Okay, so given that the my title goes with the Kitaev materials, so I think I have to define what is the Kitaev material. So I'm going to define a Kitaev material as the material, solid state material that has the Kitaev interaction, which is a leading term in a full Hamiltonian. And I'm going to call sub-Kitaev materials where the Kitaev interaction is going to be sub-leading term, but the physics of this will be probably governed by the other interactions. Okay, and then the main question that I want to ask for the today as well as the tomorrow is going to be the basically, does this Kitaev materials has the largest Kitaev interactions? On the other hand, are these Kitaev materials governed by the Kitaev physics? So what do you mean by the Kitaev physics is something like this, which we have been using quite a lot. So here is the vertical axis is the temperature, and the x-axis is the some interactions. Where I just put it as a Heisenberg, but in reality, this can be other interactions because these materials are not just as pure Kitaev. There are other interactions that comes in, generate some kind of magnetic order here. And then we are nearby the Kitaev spin liquid, which are well defined as only a 0 temperature. And it's a two-dimensional material, so expect that there will be no phase transition, but this probably transforms into some kind of mixed state. And then the finite temperature here, where the dashed vertical line is we hope that our material is sitting in. So here's my material at a low temperature has the magnetic order. And as you increase the temperature, we might have some kind of physics, which are kind of governed by the zero temperature Kitaev spin linkage. So that's the kind of picture people have been using. I'm not the first one. But my question is that it's actually at t equals 0. We're not only seeing a zigzag order. So I have these other parameters where the other quantum parameters such as magnetic field, which has been a hot topics in recent years, or some other interactions. We expect that this zigzag order will compete with some other interactions due to the other interactions, some other state here. Maybe this Kitaev spin linkage might extend it here. Then of course, at finite temperature, we'd expect that, okay, whatever the phase space here is going to govern my finite temperature. So maybe these materials are governed by, indeed, by the Kitaev physics. Well, that's not, in fact, quite true. If I have other state here, and that state could be ordered or could be disordered, and this is unknown phase, I'll call it X. And then there is a transition between the Kitaev spin linkage and this unknown X, which is disordered, for example. In that case, this physics as at the material here is not necessarily governed by the Kitaev spin linkage physics, but could be governed by the physics of the X, because it really depends on how this phase boundary will appear at a finite temperature. Then my material is going to be governed by this rather than the Kitaev spin linkage. On the other hand, it's not very clear what is this line here, whether there is indeed a phase transition between this, whether that phase transition is a trivial one or is the topological phase transition between the two, is none of this is known at this point. So that'll be my main question. And yeah, so that's the goal. And we will try to see how far we can achieve to understand the physics of the material. Okay. All right. So I'm going to start with outline here. Basically, I'm a fan of the EPL, Basic English Premier League. And the modern football is the essence of them is the build up. You have to start from goalkeeper and then build up and then get the goal into the other side. So that means that we have to build up to get that main question and then try to get the goal. And before I build up, I'm going to do a warm up. So lecture 1 is basically warm up. And that is going to do some of the introductions. So I'm going to start with something really, really warm up, just running to warm up our body, basically magnetism and quantum spin linkage. And then I'll just briefly go with a couple of slides about the Kitaev interaction, because this is pretty well known by now. And I'm sure that many of you have heard more than a few times. Then I'll talk about the Kitaev material. And today I'll be mainly focused on the theory part. So first one is a microscopic understanding of this bond-dependent interaction beyond the Kitaev. So in material, we are not going to just see the Kitaev interactions, but other interactions which are non-standard ones. And that will make our life rather challenging. And then I'll discuss about the symmetry of this generic model, and then what is the strategy to extract the Kitaev interaction out of the full Hamiltonian. So it's mainly a theory. And then tomorrow, I'll talk about a lot about the materials. So that'll be our build up here. So it's a material and experimental progress. It's a short review on the mainly focusing on the alpha ruthenium trichloride. And then I'll convince you that the physics of the ruthenium chloride 3 is, in fact, there are two dominant interactions. One is Kitaev and the other is so-called gamma interaction. We'll learn a lot about what is the gamma term look like. And then we'll talk about the effect of magnetic field. So Kitaev press the field, Kitaev gamma model press the magnetic field. If you have a time left, then we'll talk about higher spin models. So up to this point, it'll be all about the spin half, basically a doublet. And then we'll talk about higher spins like spin out 3/2 and so on. Then we had some talks from Radu yesterday about the cobaltate, honeycomb cobaltate will be falling into this category, I believe. And then we'll all summarize. Okay, so let's begin with the magnetism. I mean, if you open up the textbook of magnetism, magnetism is a quantum physics and just electron-electron interactions. And this is simply, we had heard a lot about Hubbard model. So you take one electrons and put it into here, of course, the energy of U, and fermions would not allowed to have two different spins, two same spins with on a side. So we end up with an exchange interaction, which goes as the T square over the U, and the Heisenberg interaction is going to be the one we'd expect. You don't need to go through that microscopics. In fact, I can just write down the Hamiltonian based on the symmetry because Hubbard interaction is a local and has a huge symmetry. And my tight binding, hoping between a two site with a one orbital with one spin, it's SU2 conserved. So only interaction that I'm going to expect is going to be Heisenberg interaction. So you can just write down the interaction based on the hoping parameters and interaction of the U. But when orbitals and spins are not conserved through the spin-orbit coupling, any small finite spin-orbit coupling, it really doesn't matter. We have to extend our spin model in a symmetry form like this one here, as we discussed from the Radus talk yesterday. So this is going to be a matrix with a 6 component, which are unknown here. And the symmetry of the model will constrain the matrix element. So in principle, if you have a honeycomb model, honeycomb lattice with the spin-orbit coupling, of course, every material has a spin-orbit coupling. So in fact, we will have Kitaev and other interactions which are allowed by the symmetry. However, that is not sufficient enough to understand why the one term is larger over the others, such as why the Kitaev interaction is larger. And if I desire to make a sample where the Kitaev interaction is the largest, then we need to understand some microscopics on that. Before I do that, I'll talk about a little bit about the Heisenberg model, where the quantum spin liquid is best understood. Okay, so if I have an antiferromagnetic Heisenberg model, which is a SISA, and I'm solving a problem with the 4th site. So here's a 1, 2, 3, 4. And I can write my singlet instead of solving this. It's actually easier to work on the singlet. So here's a singlet, which is a site I and site J. I'm going to represent in terms of this blue oval here. It's going to be up, down, minus, down, up. And the ordering is I and J, and that's the singlet. And I'm going to introduce the so-called bond operator. And that bond operator is the half minus 2 of SI dot and SJ, and that will call QIJ. So this QIJ, if you write the SI dot and SJ, can be written in terms of QIJ with some prefactors here and then some constant added. And this QIJ is going to be an eigenoperator of that singlet. So in other words, if I put the QIJ acting on the singlet, I'm going to get a factor of the 2 and then back to the IJ. And if this bond operator acting on the other bond, for example, IJ and KL, it'll actually switch my partner of the singlet. So QIJ acting on IJ and KL, well, actually JK acting on IJ and KL, it'll generate the JK and then Li. So picture is called the Rumor diagram. And so if I have a 2 singlet, which is IJ 1, 2, as well as 3, 4, and I put the Q23 here, operator acting on this singlets, it's going to change my singlet partners to a 1, 4 and 2, 4. So this is called resonating between the 2 Rumor diagrams. And that is the idea of the LBV. So this is resonant valence bond. One can solve the ground state. And the ground state is basically possible combinations of the 2 singlet. So that will be my ground state with energy of minus 2J. And if you compute the expectation value of this spin, we got a 0. So this one has no magnetic order. And on the other hand, it actually knows that there is an antiferromagnetic correlations, which, in that sense, it's just 1, 2. So I got some numbers here. Okay, if you extend this into the 4th site to a 6th site, 8th site, whatever the numbers, and then one can find that this LBV with the different lengths might show up. Of course, the weighting of this singlet will be smaller than the weighting of those singlets, but I can cover my entire lattice with the singlets. And then degeneracy will grow as macroscopically. So the number of the degeneracy will grow as the 2 to the n and divide by n. It's like ways of finding this singlet covering on an entire size of system. It's stuck. Oh my gosh. Okay, my computer does a lot of stuff today, and I don't know how can I move now. All right, so I have to escape.
Your control panel for Zoom is on the projection on the second screen.
It's right here.
Now it's on the screen. You're looking at your mouth. Almost there. Yes, yes, yes.
And then I have to stop share. And then let's see if I can move. Okay.
Stop the share.
Now I lost the people here. Let me see. I even lost my mouse now. And you don't see either any of those, right?
Somehow you switch the main screen to the side screen.
Somehow I was able to do that, I guess. I see. So I see the zoom in here. Wow, someone has done something very
Stop sharing.
I am stop sharing. No, am I still on the Zoom?
No, you play your
Okay, but I'm not in Zoom now. Yeah. So something has happened. So I'll have to do this again. So I'm going to share the screen again and then put it in here, share, and then play. Okay, good. So okay, good. So here is the LBB was in fact suggested back in 1973. And in fact, that if you take the thermodynamic limits, we often see the spontaneous symmetry breaking, and that is basically antiferromagnetic orders appears, and that's what it is. So the our long thought of the quantum spin liquid, in fact, goes back to the like 1970s. We are looking for a quantum disorder state, dimensions higher than 1D, and the fractional excitations are, in fact, it goes, it has a long history traced back to even a one-dimensional systems and so on, and that will exist in this quantum spin liquid. And this is the examples of topological order, and that's a modern concept, which has to be described by the long-range entanglement. Okay, so the idea of getting into the quantum spin liquid was in the past was mainly trying to get it from a geometrical frustrations to avoid that the magnetic order. We like to have those kind of singlets or one kind of the topological order is covering all of our lattice. So that was the idea. But then they comes with the different shapes. And I think that these are still very hot areas, especially with the Gomez and so on. All right, and the different angle came from the this Kitaev interactions, where the Kitaev spin liquid, I will have just a couple of slides on this, basically having a bond-dependent interactions. If I write down this interaction in terms of those matrix element that I give you, that's Jij matrix element, the bond here on a honeycomb is going to have a form of interaction where this part is only finite. On the other hand, Z bond here, this Jij matrix will have only ZZ component to be finite. So it's a very special kind of the interaction. And this was, we'll call the bond-dependent Ising interactions, where spin is not kind of frustrated, know which direction they want to point. Is that going to put it in an X direction or a Y direction or a Z directions? And due to this frustration, which are different from a geometrical frustration, we will have a disordered state. And not only disorder state, this problem, as shown by Kitaev, generate the emergent particles. And this is the Kitaev's original paper. I didn't change the notations just to represent his own papers here, where the spin is written in terms of 2 Majorana fermions here and the B and C. One can show that this Hamiltonian is going to be written in terms of this Aij, which takes the Kitaev where he writes as a J. So I'm going to just respect his notation up to this slide, and I'm going to use into the K later on. So this is the Kitaev interactions, and the Uij is going to be it's a bond operator. So here, this is different from the bond of Qij. It's a Uij is the definition of the B. This Majorana to another Majorana on the bond. So it's written in this format here. Okay. And one can show that, well, actually the Kitaev will show that this bond operator in the ground state is going to take a number, which is 1. So this will take some expectation values. Then this problem is just bilinear C Majoranas, and one can solve exactly. And that exact solutions of the ground state is called the G2 spin liquid, where the G2, meaning this Uij values, can take the value of ±1. And then Majoranas are going to take the free fermions moving around on honeycomb lattice. And we know how to solve because the fermions on a honeycomb lattice will have a Dirac dispersion at a K point. So that'll be the ground state. And furthermore, in his original paper, it was shown that the smoking gun experiment, which is on the top in here, is going to be the thermal Hall conductivity. So if I apply the magnetic field along a direction where this Hx, Hy, Hz is finite, so one can try 1, 1, 1. One can try Hx, Hy, Hz. If you try the direction of the field to be 1, 1, 0, for example, X, Y, Z coordinate, then this term is 0. So we are not going to see any effect of thermal Hall. But if you have any finite values of X, Y, Z, then this interaction is going to generate the gap in the bulk excitations. In other words, those Majoranas at a K point is going to acquire a gap. And the Etsy is where the boundary will carry the conducting, well, in a sense, it's a thermal conducting because Majorana does not have charge, does not have spin. It only carries entropy. So we will have some kind of conducting Etsy mode, either this way or that way. And since it's a Majorana fermion, not a complex fermion, we'll only have the half quantized half value of the thermal Hall conductivity. So that was a smoking gun experiment, which was predicted by the Kitaev. Okay, so that's probably more than enough for just the pure Kitaev. Now, Kitaev material, as I said, in solid state material, it's in fact, we are not going to see only pure Kitaev model. We will have other interactions that pops up, and we'll have to see how we can get the largest Kitaev and why that's the case. If I want to get that directions, what am I supposed to tune it? So we are going to go through some microscopics here. So we are going to prepare the honeycomb multi-insulators. In other words, we are going to deal with transition metals where strong electron-electron interaction is needed to begin the process. And then we need a bond-dependent spin interactions. In other words, I need to break that SU2 symmetry. I need to go beyond the Heisenberg model. So I need a Spinozzi coupling to help me to get it into such interactions. Okay, the first generation of the candidate materials goes back to the iridate. So this is the sodium or lithium. It's called alpha iridate, alpha iridium here. It has a layer structures. In between, the A is corresponding lithium or the sodiums. This has been studied in many others. So that's the one generation. And later on, it was a second generation pops out, and that's the transition metal trihalide. So it's an MX3 here. We begin with the ruthenium, and I'll tell you why the ruthenium is the best candidate and where that idea comes from later on. So ruthenium trichloride, which comes with the layer of the honeycombs, and the layer stacking becomes rather important in terms of the understanding the material itself. So here's a ruthenium which is surrounded by the chlorines, And since we don't have that alkali metal in between the metals, these are van der Waals material. It's very easy to clip, but that generates a lot of complications. Okay, all this candidate that we have said, in fact, has a magnetic ordering at low temperature. So as I said in the very beginning, that this x-axis, where other interactions comes in, and that will generate the magnetic order. And then there is a finite temperature, which might be governed by the Kitaev physics. So let's see if that's the case. Okay, so let's think about the microscopic derivations. This is only for a spin half and bond-dependent interactions, and we'll talk about the phase diagrams and where on nearby phases nearby the Kitaev spin linkage. Okay, so this is a J-effective half spin-orbit coupled doublet, and we'll be mainly focusing on the octahedra group, the one that is cased by the octahedra p orbitals. So we begin with some 5d orbitals here and filled by the d5. So this will be corresponding to up, and then down, down. In other words, this crystal field splitting is the largest energy scale, apart from the atomic energy levels here, other atomic PD and so on. So this is the largest. And then Hund's coupling comes in because the crystal field is larger. We are going to have up, and down, down. We are filling out 5 electrons in the T2G. That will be D5. And then spin-orbit coupling comes close to the Hund's coupling. It does not necessarily have to be smaller or bigger. I mean, they can be comparable to each other. And in that case, we will have a splitting of this T2G splitting into the half and 3/2, because L effective is -1. In fact, the half and minus 3/2 is going to reverse in terms of energy levels. And we will fill up all of the 3/2 and have only half. So this physics of the half field J-effective half band, in fact, works for the layered perovskite, as I said. It's the 214, also has this physics, as well as it's atomic physics. So it really doesn't matter what lattice you have. It's one site surrounded by the p orbitals.
Question.
Yeah.
In principle, exactly the same kind of splitting could occur in the first row of the transition metal series, but of course the lambda will be smaller. How
Yes.
big is lambda spin-orbit coupling in the iridium?
Yes, that's a very good question. So in fact, that you can have a 3D, 4D, 5D, all of the spin-orbit coupling will occur, and this physics will apply in all of them. Now, energy scale comes to play. So if I have like a 3D, yes, you will split here. And so the lambda in the 3D case is going to be about the 20 MeV, roughly. So it's not a small energy scale. And if I have a 4D, it's about 100 MeV, like ruthenium will be about 100. And then if I have a 5D, iridiums will be about like a 400 MeV or 500 MeV. So they're very large energy scale. What screw up this physics is the next energy scale, which is a trigonal distortion. Or you to have a C2M where the monoclonic distortion comes in. So when you have a material, you have a slight distortion of the this octahedra case. So in an ideal situation, this physics hold, doesn't matter whether you have 3D, 4D, or 5D, but the trigonal distortion comes in and the trigonal distortion start to mix them up. So you're not going to get the doublet, which are made out of J-effective half. You are going to get a doublet, which are mixed up of these two, and then you are going to lose the spin-orbit entangled wave function. So in the 3D case, trigonal distortion is about 60 MeV, for example. Then the trigonal distortion is larger than the spin-orbit coupling, and this physics need to be rather carefully examined. While in the 4D and 5D, lambda is much bigger than the trigonal distortions. And there we have safely assumed that my physics is described by this J-effective half. Then you can ignore the rest of them. Yeah. Okay, so then if you're starting from here, so the next slide is showing you the wave function. So I keep talking about the wave function because that's the building block of the whole of this physics. So we have d orbitals of the entangled, meaning that spin and orbitals are now mixed through the spin-orbit coupling. So without spin-orbit coupling, we are not going to get any of this physics. And then bigger the spin-orbit coupling, I'm going to get a bigger this bond-dependent interactions. So here's my J-effective half. It's mixed of the red and blue, and where red and blue spin up and spin down. And this is basically XY orbital. And then we have this blue ones, which make mixtures of XZ and YZ, and comes with the imaginary I here because it has a finite angular momentum. So it has a finite angular momentum and a finite spin, and mixtures of those is going to make my wave function, which is a effective half. And the other one is the one can get it by time reversal, and my screen is again frozen. So I have to escape again. I'm sorry that this is keep happening. Let me play again. Okay, good. So I don't have to stop the share at least. Okay, I'll just escape and come back. And the other J effective minus half, you can get it by the time reversal operation. And so colors is going to change, as well as angular momentum has to change to a -1. So that is the basis of my wave function. And it's frozen again. Do you see my mouse?
Yeah.
Yeah, but I don't see the mouse, and I don't know how to get out of this now. Oh. Yeah, because my mouse doesn't show up on my screen. So yeah, it's there, but I don't see them. So I don't know how to escape here. So I think I have to stop share this time. No? It's, yeah, the mouse is moving, but it's frozen. So I cannot move to the next slide.
No, you can move the mouse back and restart your PowerPoint display.
Where is the PowerPoint? Okay, so I actually had to use my fingers to move it. This is little, I never had this experience. In any case, sorry. Oh my God. Okay, so where I was. Okay, so I have that doublet, which has the nice colors of the blue and red mixed. But when you're doing when I'm doing a process of the building so that was atomic site. It's a single site problem. So I was talking about the J effective half on a single site here. I need to build up the spin model between the, say, the nearest neighbor. So between these two, that means that my Hamiltonian, full Hamiltonian, I'm going to begin with this one, which is covered by the, for you, it's covered by that little thing here. Yeah, let me see if I can move it down in somewhere here for the audience in the room here. Yeah, so here's my multi-orbital on-site interaction. So it's a two-site. I have Coulomb interaction and the Hund's coupling here, which is going to generate the S sphere as well as Li sphere. So this is going to be a multi-orbital called Ganamori interactions, where we have ignored the easy orbitals in this picture. And then what we have to do is that we have to connect the two sites, and that connection is through the hopping parameters. And there are three kinds in this honeycomb lattice. One can show without the distortion, without the trigonal distortion. In fact, that this part is 0. The basis here is going to be XZ and YZ and then XY. So we have a T2G orbitals, which are hopping between the site. It's not the J effective is hopping. Indeed, they do, but it's difficult to write them down in terms of J effective half because you have to involve the J effective 3 half in this process, virtual process. So we are going to write down the conventional hopping in the T2G basis. And as I said, these are going to be 0. And you can see that, in fact, that this is XZ and YZ here, and this is XY orbital. So XY orbital, think about these two here, and one can show that due to the mirror along the z-axis, in fact, along one of those directions, in fact, one can show that this is the forced by the 0 by the symmetry of the lattice. Anyway, so there's a T1, T2, T3, T1, T2. Actually, this T1 is equal to each other because XZ and YZ are identical on one of this bond. This hopping here is going to be a dominant ones because the p orbital is the closest to the d orbital, and this hopping is represented by T2. Okay, and that's going to play the very important role. So bear in mind. Now, okay, there we go. So now the effective spin model, low energy effective theory, will be then basically looking at this Tij, write them, doing some perturbation theory here, and project on the alpha beta, where the alpha beta is going to be our doublet, spin out, spin half. So that's the whole process. Okay, so here is one bond. Let's pay attention in a one bond, two side problem. So we just work on the two side, and the rest of them will use the symmetry to get the interaction form. Okay, so focus on this bond here. I'll call that Z bond, and that Z bond is going to be the one that is our focus. So I'm going to amplify that point and then try to see what happens. So the first thing is, as I said, the process that dominate in the material is going to go through this p orbital here. So this is the super exchange or indirect integrals or indirect hopping is the one that dominate. And one can see if I look it up, there are 2 process. There's one from up and one there is a down. It really doesn't matter. So here is the XZ and YZ combination, LZ equal to 1, and here is LZ equal another 1. And we go through this process, it's called TPD pi, and it's a dominant hopping integrals, which often we write as a T naught. It's going to be TPD pi square divided by atomic potential difference between a p and d orbitals. Okay, good. So then remember that these guys are made out of those. So we have to think about all the T2Z orbitals, how they hop around. And this interaction, this is called T naught, is going to be the dominant ones. Then, as I said, there are two processes. One is upper here and the other is down here. And among both of them will give us a finite spin interaction. On the other hand, on this Z bond here, p orbital going through the indirect hopping is forbidden. And the reason for that is because xy here, and this is a pz, and pz has a plus sign here, minus sign there. So in fact, that this xz and pz is going to be a 0. So there is no hopping between the xz and pz here. Of course, there is a direct hopping between the xz and xy. So this xy will have direct hopping, but that will be again Heisenberg interaction. So that's not what we want. In fact, we want this p orbital, the hopping process that go through the p orbital, and that will be the one will generate the Kitaev interaction. So let me move this up here, try to show you some of this important process. Okay. All right. So if you look at the this two here, this process, remember that the xz and yz are part of the LZ equal to 1. And if I hop from the yz to an xz, one can show that this process have to change the angular momentum of the plus minus 2. Yeah, because they are falling into different jz equal to, this is a plus minus. So one can show that this process requires to change the angular momentum of the plus minus 2. And I'm not flipping the spin. So spin is not going to be changed. That means that my delta Z effective has to change by plus minus 2. So by the symmetry, I can tell, well, this process does not allow the Heisenberg term because Heisenberg is going to be a SU2 symmetry. So that won't allow to have a Z going to change by plus minus 2. So I can immediately tell that there is no interaction such as Heisenberg. On the other hand, this process will now involve, okay, now even this doesn't work. Yeah, it has to involve the higher state. Let me put it here, down here. Let's see if I don't need this space here. Okay, so I put it down here. So this process of the T naught, in fact, involves a higher excited state where Jz equal to a plus minus 3/2. So you can see that the change of plus minus 2, meaning that I can change plus minus half to a plus minus 3/2. So the intermediate state through this perturbation theory have to involve the J-effective 3-half state. And they are separated by U minus 3JH or U minus JH. That depends on how I align the spins. Whether the spin goes up here together with up or above down here, we'll have two different intermediate states. And if you take that both of them into account into the virtual process, that we end up with this Kitaev interaction here. So then this Kitaev interaction comes in because it only changed the delta Z by ±2. So you can see that, well, that interaction has to be SC-SC. It's an Ising line. And this one is going to be proportional to the Hund's coupling here because this two intermediate state is necessary to get this interaction. And difference between the two is the what generate this interaction. So Kitaev interaction requires to have not only finite spin-orbit coupling, but also the Hund's coupling, as well as the T-naught here. Okay, so that's how we can get the one bond of the Kitaev, the Ising interaction. So I end up with, in the Z bond here, I end up with SC and SC. Oh, that's very nice. And if I do another one, the X bond, all I have to do is that instead of working on the XZ and YZ orbital, the X bond, I just have to work on the XY and then XZ orbital. You rotate everything by the C3. This honeycomb lattice has a C3 symmetry along the Z axis. So if I rotate with the out of the board or out of the screen, rotate by the 120, Z become an X, X become a Y. So by doing so, one can get that the XZZ bond become XX bond and this become a YY. So that means by looking at that process, we end up with the Kitaev interaction. So that is basically the microscopic way of getting the Kitaev interaction. So this means that if I only have a p orbital mediated hopping, you just have a Kitaev, nothing else in the T2G with the spin-orbit coupling and finite Hunds. This theory, in fact, that this was going back, I just want to show you historical ones. You can see this bond-dependent interaction in one of earlier papers. In that papers, it's a triangle lattice. In fact, it's a cobaltate with a small trigonal field. So I have a very little trigonal field where delta here is a trigonal distortion strength, smaller than the lambda. So it's a 3D material. Then you can see that you can write this in terms of Heisenberg and Kitaev. So it's quite ubiquitous. It's very easy to get it, but whether that's dominant or not is a different story. So why that's a different story is because we have other interactions that can be generated, not only just direct hopping, not only the indirect hopping through the P. As you said, there is a direct hopping here. And that direct hopping between the orbital and spin, I'm not changing orbital. Orbital is conserved, spin is conserved. Okay, I end up with Heisenberg interaction. So that's one interaction that exists. In addition to that, we have also another interaction, which has been missed in the earlier stage, was that one can go through two processes. I call it interference or kind of a mix between the two. One process, I go through the direct hopping to the T. Another coming back, one can go through the this T-naught, which is the p orbital mediated ones, and that generated the gamma interaction. It's not a Zalojinsky-Moria interaction. If I have a minus sign here, that will be Zalojinsky-Moria with the d vector along the z-axis. But it's a plus because I don't break any inversion symmetry. So Zalojinsky-Moria, nearest neighbor here, is forbidden, but it comes with a symmetric off-diagonal interactions. Again, it's involving this intermediate process through the p orbitals with involving J-effective 3-half state. So this gamma is also proportional to the Hund's coupling as well as this p orbital mediated hopping process. Okay. All right, so I just want to emphasize that this is going to be one of the important terms to take into account if you want to understand the ruthenium trichloride. So just want to say that little bit about this one. We'll come back tomorrow again, but this gamma interaction, if you look at it, it's bond dependent. So when the Ising Z bond here Kitaev is an Ising interaction, so Z bond will take SZ and SZ. In that bond, gamma interaction will take XY, YX. And if I do C3, if I have X bond here, the excess SX of the Kitaev gamma bond will take YZ and ZY. So if the Kitaev interaction is a bond-dependent Ising interaction, gamma interaction is a bond-dependent XY interaction. So it's quite frustrated. It's even more frustrated, and I think it's more frustrated than the Ising interaction. It's not exactly solvable problem. Many people attempted and failed, well, including myself. It's numerically even difficult problem to check. Yes, please.
So, is there something we can do to view the higher levels of the connectors of the P orbitals, etc., view the relative strength of them?
So relative strengths of the gamma interaction
Versus
versus Kitaev. Yes, in principle, one could, because I'm showing you the most, how do I say, most essential terms. In real life, there are much more complicated. And yes, in principle, one can tune the some of the coping integrals to get a gamma to be dominant. But in general, if I have a PD orbital, the strength of the T naught, which is indirect coping, is the largest, then we expect that the Kitaev to be negative, which is ferromagnetic. And then strength-wise, it's going to be a largest. And then gamma, we expect it to be anti-ferromagnetic, which is a positive sign. And then it'll come as large as Kitaev or subdominant. And then Heisenberg will come with many different paths, and they cancel each other. So Heisenberg will become very small. Well, in fact, Heisenberg doesn't appear if I only have a PD hoping. Yeah, in this doublet. Yeah.
There's also no fine-tuned point that gamma is equal to Kitaev, so that it becomes solvable.
Yeah, so that one is you can fine-tune the problem. You can fine-tune it, for example. And I think one of this lithium, iridium, lithium 213, I think that one is probably closer to that point where the spiral order appears. It's so if the Kitaev is equal to gamma, then there's a hidden symmetry that one can show. You include the 6th site, and one can show that that maps to the SU2 again back to the Heisenberg model on a 6th site. So you can solve it exactly at the K equal to gamma point. But that will be really a fine tuning. And I don't think any of materials sitting exactly at that point. But I think lithium is the one that is close by. While the other two, which has a zigzag order, is very different physics. Yeah. So luckily, we end up with this two bond-dependent interaction, and Heisenberg interaction will become rather small. So let's look at the phase diagram now. So here's the ideal. Again, I keep emphasizing this because real material is none of them are ideal. So you always have a small things to worry about. So here is the ideal case. We have 3 terms that are symmetry allowed. There's nothing else. And then there are 2 bond-dependent interactions. One is the Kitaev and the other is a gamma. And then there's a Heisenberg interactions. And this is just writing a 1 bond. And as I said, you can get the other bond by just rotating by the C3. So let's look at the phase diagram. This was earlier ones by the 24th site ED calculation. We are just looking at a one antiferro gamma, which is more relevant. And this is drawn in a circle in such a way the boundary here is going to be Kitaev Heisenberg model. So angle, the way that I have represented, the phi is going to be controlling the Kitaev and Heisenberg. So here is an antiferro Heisenberg. Here is a ferro Heisenberg. Of course, this phase will be dominated by antiferro ordering and the ferromagnetic ordering here. As I move along the north pole, it's going to be antiferro Kitaev. Moving to the south pole, it's going to be ferro Kitaev. As I'm marching towards the center, this will be a pure gamma model with antiferro gamma, which is much more frustrated than the ferro gamma interaction. So that's what it is. And in addition to antiferro and ferro interactions, the ordering, we have other type of orders that appears, One is this zigzag order, which is appearing at the antiferro Kitaev and Heisenberg Heisenberg. So that's a zigzag. And that's the one that is found in the most of the samples, by the way. And then there's a stripy orders here. And there is a so-called 120, which has this 120 along the triangle. So second nearest neighbor triangle form 120. The other B sublattice form another 120. And relative angle between the two are not fixed in this 120.
So in these exact diagonalization studies, do you always use periodic boundary conditions? Because
Yes.
If you think of the Kitaev, right?
Yeah.
For some sites, you just cut off one bond, and
Yeah.
then the frustration. is
Yes,
gone.
yes. So if you do so first of all, this one is use the periodic boundary condition. And you're right that the Kitaev here, these two are going to be seriously affected by the boundary condition as well as finite size. But on the other hand, you can see that these two are extremely narrow anyway. So that's the one thing.
How do they deal with this? There are also a lot of DMRG studies, right?
Yes.
Where they look at Kitaev ladders and so on.
Yes.
How do they deal with this problem there?
Yes. So I didn't prepare for the quasi 1D ladders and chains, and there are studies on the chain and ladder, and they're very interesting as well. And that will also have some boundary condition that pops up. In the purpose of this one's, I think 24 site or even 32 site, the Kitaev that appears a tiny area here and a little bit elongated there is rather generic here. So I wouldn't worry so much about how far they extend. They are tiny in the phase space. So this is extremely narrow range of Kitaev spin linkage, and that was the T=0 phase diagram. And on the other hand, if our order state, such as a zigzag, is nearby the Kitaev, our finite temperature may be governed by the Kitaev physics. So let's see. Now, so here's a ferro Kitaev and here's an anti-ferro Kitaev, and we believe that the most of the compound, including this iridate as well as ruthenium chloride 3, is sitting here actually. So that means that it is a dominant PD hopping, which will give us the ferromagnetic Kitaev, and then positive gamma. It's already a positive gamma here. It is sitting somewhere here, and this is mainly unknown, which I call that X here. Okay? It has a correlations, just like RBB. There is no, we can't identify magnetic order within this finite size. Of course, who knows, some of this might be competing and then might be generated. But you can see the correlations of ferromagnetic correlation somewhat here, but it has a yellowish here. Do you see the yellows coming down in here? So it has a zigzag correlation. So that means that this unknown X has some ferro as well as spiral type of the correlations are building up, but none of them are ordered within this numerical study. But that means because the zigzag correlations are built in already, if I have a small interaction, that may help to stabilize the zigzag order, and that will happen. And that's why this materials does show a zigzag magnetic order. And that's an important point because later on, we'll look at the material under the magnetic field. And then because the zigzag is set by some other interaction, which are not even in this ideal case, and we can destroy it and then get it into some other phase. So what is the type of the other ones? And that is this trigonal distortion, which plays the very important role. I'm going to cover up here. So if I just stay on the nearest neighbor models, in this case, if I have another interaction, which is called trigonal distortion, and that generates another bond-dependent interaction, which is called gamma prime. And remember that I had a 0,0 in the T2Z tight binding, and that is not allowed by the trigonal distortion, and that generates this gamma prime. But trigonal distortion has to be smaller compared to the spin-orbit coupling to have this physics to be valid. Once you have a much larger, then this will be broken down. And of course, we will have to think about what is our doublet to be made out of. Okay, so within this area, when gamma prime is negative, in other words, ferro-like, then you can see that a lot of this phase is now covered by the zigzag order. So correlations were built in, and I can just stabilize the gamma interactions. I thought that I was covering the my reference, but actually I'm not covering my reference, it's someone else. So I'm going to emphasize that there's a nice work by other peoples too, that instead of this trigonal distortion, one can also add the third nearest neighbor Heisenberg interaction, J3 here. Then we can also stabilize the zigzag order. And those are the minor interactions. So zigzag order is there in the ruthenium criteria as well as sodium, iridium 213. And they are probably, the energy scale is different between the two compounds, but one can basically kill it and see what we are going to reveal. So that is going to be a part of tomorrow's talk. And I just want to go beyond a little bit about the symmetry analysis and then how to extract the Kitaev interaction out of it. So to look at the symmetry of the lattice, there is a way to tune the JK gamma interaction into a slightly different way. So look at it in a slightly different way, and symmetry will help us what should be finite, what should not be finite. For example, we'll talk about the thermal Hall conductivity later on. And can I get the finite thermal Hall? Yes, you do in a certain magnetic field. No, you cannot in a certain magnetic field because you don't break some particular meters and so on. So that will be an important aspect. So to look at the model, because now we are going to connect to the actual material. Materials are not made out of this axis. So the axis that we are saying X, Y, Z, the X, Y, Z are determined by, because we begin with atomic site. In an atomic site, I can coordinate them unless I have environment. And that environment is provided by this octahedra. So this octahedra case that was given to us, and that we call that XYZ. So you can see the XYZ, which is made through the direction of my p orbital, where the p orbitals are sitting in. But that is not very convenient. If I do the experiment, I want to apply the field in the outer plane and the in plane. And they're not in the XYZ. They are in the ABC crystallographic axis. So I'm going to call A direction. This is the conventionally used. A is 1 in here, by the way. So A is going to be perpendicular to the bond. We have this XYZ bond. So it's a perpendicular to one of the bond. You can choose that direction. If I have R3 bar, which is the 120 rotation symmetry is preserved. In other words, C3 is there. Then you can choose this perpendicular to the Z bond, perpendicular to the X bond, perpendicular to the Y bond. It is the direction that is perpendicular to the bond, one of the bond. On the other hand, A-axis here is going to be the direction which is a parallel to the bond. So that's going to be A-axis. And C-axis is outer plane. So that's the probably most easiest. If you want to connect this ABC coordinate into the XYZ, we just have to rotate this. So A-axis will be 1, 1, minus 2 in terms of XYZ coordinate, which are made out of octahedra. And the B-axis will be -1, 1, or 1, -1, doesn't matter. Its inversion is there. And then C-axis will be 1, 1, 1 direction. Yeah. So when I say 1, 1, 1, it just means that it's a C-axis. Okay. So if you use that coordinate, how the model is written up, and that goes back to actually early days. This Hamiltonian was mainly used in a particle lattice. I just have changed a little bit of the notation because this, I call it JAB. I believe in this old paper, it's called J press minus press minus. JAC is called JG press minus. So these are just changed a little bit of notation. If you go back to this very nice paper by Guignat and collaborators, they call A here and then call the B here. So it's a slightly different notation. I don't know which one is the best because none of them I like, but on the other hand, I don't want to call just the unknown A and B. So I have changed into JAB and JAC. Since I just rotate the coordinate, of course, these are related by the original JK gamma. Now this JXY is going to be XY model. Z is an Ising interaction along the, so if I just have this tree, it's an XXZ model. Okay. And then JAB here is a bond dependence is now embedded in the phi here. So phi gamma is going to be 0 plus 2 pi by 3 and 4 pi by 3 or minus 2 pi by 3. So depending on the bond, so JAB, JAC is depending on the bond. JXY is going to be J plus AAC, and then Z is the J plus AAB. Nicely, the JAB here, JAC here is related by K plus gamma or K minus gamma. What's nice about this is that if you put it into this coordinate, now if you look at the difference between the XY and Z, so I just subtract the two, JZ minus JXY. If I subtract these two, Heisenberg cancels out. And that should be because this is telling us it's anisotropy in plane versus out of plane anisotropy. So in plane and out of plane anisotropy, Heisenberg is not going to be there by definition. It depends on the JAB and minus JAC, and that's proportional to just the gamma. So gamma interaction is the one that will give us the in plane and out of plane. If the gamma is going to be antiferro or positive, that means that Z-axis, here the C-axis, by the way, it's out of plane, is going to be hot axis. And that's what we see in the ruthenium criteria. For example, if you look at the susceptibility, I'm going to show you tomorrow, a lot of data, experimental data comes tomorrow, that the anisotropy is huge. It's a very two-dimensional. And if the trigonal distortion is 0, it's an ideal model. I don't expect the G factor to be very different. In fact, that in the atomic physics, it's basically 1. There is no anisotropy. So that anisotropy will be mainly coming from the gamma interactions. So that's the one thing to bear in mind. And another symmetry that one has to look at it, that's related to the which direction I put the magnetic field to get the finite thermal Hall conductivity and so on will be depending on this. So can we extract the Kitaev interaction out of this full Hamiltonian is the question. By the way, how am I doing in a time? Yeah, we're already in discussion. Okay. Yeah, so I think I have few more slides and I've been spending a lot of time on that. So if you have questions, please do interrupt me. I think we can be in the mode of discussion. Okay, so one of the symmetry that's very important, and some people use pseudo beater. It's basically a rotation of the 180, 100. So basically, I'm going to put a, so I put a, here is the A-axis, okay, perpendicular to the bond. So this is my rotation axis. Rotate by 180. So it's a pi rotation. It's called C2. 2A meaning 2 is 2 pi by 2, which is 180 degree. A referring to the A-axis is my rotation axis. If you rotate by C2A, and if you don't see the p orbitals or the octahedra, you might think, well, this has a rotational symmetry. Actually, that's not the case. In fact, it's not. It doesn't have that C2A symmetry because this triangle here, which is the above the screen, will map to the below the screen. So there is no C2A symmetry, which is broken by the lattice. And on the other hand, if I rotate along the B-axis, which is parallel to the bond, if you rotate by pi here, all of these points will map to exactly each other. So there is a C2B symmetry. On the other hand, there's no C2A symmetry. So I call it preserved C2B. On the other hand, broken C2A. So 180 rotation around the A-axis is not there. And the consequence of those is basically this JAC term is being finite. So consequence of C2A broken is embedded in the Hamiltonian. So my Hamiltonian, well, our Hamiltonian is going to have all this term. And C2A is going to change the direction of the spin of SD and SC take a minus, but A is going to take as it is. And the bond of phi x has to change from phi I. And one can show that in this case, JAC, this term here, is the one has to be changed the sign under the C2A. On the other hand, if you do the B-axis, it's everything is preserved. So all of this is going to go back to itself. And then JAC here is proportional to the Kitaev and gamma interaction. So the idea is that how you can separate the Kitaev interaction is using a magnetic field. So I'm going to apply the magnetic field in the AC plane. So to determine the size of JAC, I'll apply the magnetic field in the AC plane, and then rotate them out of plane as well as in plane. So this blue and red magnetic field are related by C2A. Okay, so apply the field here, apply the field there, And these two are relayed by C2A. And if I had a C2A symmetry, these two will have the same excitations. In other words, here, delta omega to K is the excitation energy from the ground state to the excited state. And I have, let's say I have polarized state. So I don't have any other broken symmetry that mix up my symmetry analysis. This will be reasonably large field that polarize the state. And I'll call the delta omega K, which is the excitation energy difference between this field versus that field. And this field is going to detect the size of the JAC. Because if I don't have JAC, these two have to be identical. So this has to be 0. Such as if I had a field in the BC plane, I had a C2B symmetry. So if I had a magnetic field that relate between C2B, I'm going to get the excitation, which is going to be exactly a 0. And I'm going to call delta omega A, which is the in-plane and out-of-plane anisotropy. Okay. So how do you measure it? This is one of the angle-dependent ferromagnetic resonance. Is the one way to do it. So here we'll come with the magnetic field, which is along the A-axis first, and then rotate them along the C-axis. So starting from the A-axis, rotate to the C-axis, and you will see the excitation will have, this resonance will vary as a function of angle. Starting from the A-axis to outer plane, this blue is going to reflect the in-plane, outer plane anisotropy, which are measured by the gamma. So that difference is going to tell us the gamma interaction. If it is completely isotropic, we'll get the flat Heisenberg-like. The resonance energy will be independent of angle. Then what we do is that we come up with the field and then rotate into the minus C-axis. So I'm starting from the A-axis and rotate backwards, and that will be a red color here. And this is resonance. Is going to have different angle dependence. And this separation between the two, red, blue versus the blue, is going to detect the size of JAC, which is K minus gamma. So I have two unknown, K gamma as well as K and gamma. If I know this one first, I subtract this out of this interaction. I can isolate what's the size of the Kitaev interaction. So that's the recipe to isolate the Kitaev. Apply the B field in the AC plane with the angle of theta, and then do the measurement of the spin excitations, and then rotate the V with the minus theta here and do the measurement of the spin excitation. And then difference between the 2 and 4 excitations will tell me the K minus gamma. But in addition to that, I'll have in-plane, out-of-plane resonance, in-plane, out-of-plane excitations will tell me gamma. Subtract gamma from the K minus gamma, I'll get the Kitaev interaction. Okay. So trigonal distortion will little bit complicate the story because if I have a trigonal distortion, which is always present, then the JAC is going to take a K minus gamma prime, while the in and out of plane anisotropy will take gamma plus 2 gamma prime. So we need to know 3 unknowns here. And in that case, we'll have to rely on the finite momentum, which is inelastic neutron scattering. The only one angle-dependent ferromagnetic resonance is a Q equals 0 excitations. Here we have other momentum point. So here is, I just choose the 30 degree, plus minus 30. Blue is the excitations with plus 30 inelastic neutron, for example, with this particular parameter, close to the ruthenium criteria, and dot, 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 other interactions. Minus 30 is the red ones here. You see the difference between the blue and red. The dots are from a 24 side ED, lines are from the linear spin wave theory. And this is the field of 1, which is size of Kitaev here. And if you make the field very large, then the linear spin wave theory and ED matches better. Okay, but you can see this clear separation between the two, and that will be the one detect the bone-dependent interaction, because Heisenberg is not going to contribute any of this difference. Okay, so here's my last slide. I will talk about tomorrow mainly the these two compounds. This is a ruthenium trichloride. I'll call it Kitaev material by the definition that Kitaev is the largest. I think I'm going to discuss a little bit about the chromium triiodide, which I call that higher spin model. It's a spin 3 half. I'll call this sub Kitaev material because here ferromagnetic Heisenberg is actually a dominant. It's a ferromagnet, but I believe the Kitaev interaction is second sub-leading term, which is under the debate at the moment, but I'll bring up some of those tomorrow. So I'll stop it here. Thank you for your attention.
For the different branches of where you showed just the slide before, where do you take the difference? Like, how do you know where to take the difference to know isolated capacity?
Oh yeah, so the one that I was talking about earlier was taking mainly a gamma point. So I was looking at that point here, but now my field is very large. So you can see that the difference is almost zero. But if you have a smaller field, you will see the difference at this point. So it depends on the parameter sets in the finite momentum. In this particular parameter sets, I believe the endpoint is the best place here. Endpoint here is going to be the best place to look at the blue and red difference with this field and that field. Yeah. And then one can do a theory. One can show that why this particular K point is very small, but that's some details.
So everything you've been discussing is about an individual layer in the 2D model.
Yes.
Does anybody ever think about the coupling between the layers?
Yes, between the layer is coming tomorrow. In fact, it's very important to understand the experiment. Yeah, because especially for the ruthenium trichloride, it's a van der Waals material, and the van der Waals potential is like less than a 1 MeV, about a 1 MeV, which is about 10 Tesla. So by the in-plane of 10 Tesla, actually a lot of things can change. So we will discuss, I hope that we discuss some of those. Yeah, C-axis is very important. Despite that it's small, but I think it's important to understand the experiment.
You showed a really interesting kind of rich phase diagram.
Yeah.
With all of the different interactions.
Mm-hmm.
Is there a lot of interest in the natures of phase transition between phases at all?
Oh, yes, that's a very good question because yeah, so I don't think with the 24 side ED, because a lot of these phases are not solvable. So it's in fact difficult to say the nature of the transition. On the other hand, some people have been spending quite a time to understand the nature of transition in a quasi one-dimensional system. So if you have here's a ferromagnet is next to the Kitaev spin liquid. In fact, if I solve the classical model, zigzag comes all the way here. So this point in a classical model is a point by the definition of classical model. And then they will meet the stripe and zigzag 120, all these things will start to meet them together. Yeah, so then the transition from here to ferromagnet, given this look like very sharp, but again, it's a finite size effect, finite size. So who knows, this might be a finite size effect. It look like a first order transition, but it can be second order. Then it becomes the story becomes very interesting, how the ferromagnetic model will tuning into Kitaev spin liquid. Yeah, so all of those transition lines here, which are with some cross, is the first transition, but 2D models are very hard to study. So people have looked at the quasi 1D chain, or there the transition has been much better studied with the 120 size with the DMLG and so on. So I think a lot of them show up as a second order transitions. Yes. Yeah. So it's unknown at this point. It's not fully studied in 2D. Yes, Ashley.
So there's been a lot of work moving beyond the field theoretic treatment of space magnetic turbulence. Classical Monte-Carlo. But there are a lot of challenges in actually arriving at the confirming the magnetic fermionic textures via these numerical approaches. I was just curious in the investigation of these materials for spin liquid phases, to what extent people have aware of these like issues.
Yeah.
With numerically confirming the magnetic fermion phases, to what extent there might be the way people are doing like exploring the phase diagram in this case,
Mhm.
so they be missing
Mhm.
this sort of physics actually because they're not doing this carefully.
Yeah, so the magnetic fermions, in fact, that if you solve this problem on a triangle lattice, so there are people, well, including myself, but a lot with other people's, I think the pioneers, others, in fact, that you can find these interactions in a triangle lattice as well. And then people have looked at what happens on this model on a triangle lattice. So in a triangle lattice, one can show in a certain phase space, there is a magnetic fermion looking. I don't know if I should call this fermion because the ground state has some kind of vortex shape. And that was been kind of detected by classical Monte Carlo. So classical Monte Carlo will tell you if I have some kind of those big magnetic structures. So they do show up in that case. So there apparently a lot of those, yes, it does show up in the triangle lattice and people have identified. Along this line, you might say, well, you're working on a 24 site. Therefore, what if you have missed bigger size unicell magnetic order? Yes, indeed, people have studied that too. I don't think I have a slide. In fact, along this line where I called unknown X, classical model shows the bigger size of unicell, like a 6 site, 18 site, 56 site, and so on. So in fact, yes, if I have a magnetic order, which were bigger than the 24 site, I could in principle miss it. And that has been studied. So, but on the other hand, that's a classical model. So what happens, I introduce quantum fluctuations with such a 24 site or 56 site unicell, it becomes unclear what happened. That can easily melt, for example. Yep.
So maybe it's a stupid question because I don't know any of the background, but if you, so you said, okay, you don't have geometric frustration if you just take the Kitaev model, but it comes through the bond directional exchange. If you take other bipartite lattices like square lattice, if you just take Sx as x along x and Sy as y along the y bonds, or do the same with Z in the cubic case, do you get long range order there, or is it also
So first of all, on a scale lattice, I'm not sure because I have full, so at a given site, I have full bond that coming out of the single site. So I'm not sure how to take Sx, Sx, Sy, Sy, Sc, Sc.
No, just x and y. So you forget about this component.
Oh, I forget
Or you
about
do the same with the cubic lattice in 3 dimensions and take
Mhm.
ZZ along. Is that correct? So what's known about this model?
For the gamma interactions, not the Kitaev interactions, because Kitaev interactions people have used in the decorated other lattice or bed, or hyper honeycombs. You can do the Kitaev interactions there. With the gamma interactions, I don't think people have attempted to look at what happens with the gamma X and gamma Y.
On the square lattice, write down the Kitaev interactions. I mean, regardless if it can be realized.
On the scale lattice, I think the reason for that, if I have just T2G on a scale lattice.
No, don't forget. No, I'm not interested in trying to
how to achieve them.
Yes. Just like Kitaev, you can just write on the Hamiltonian.
You cannot, because I need the 3 bond that's so the Kitaev interaction that's exactly solvable need to have XX, YY, and ZZ.
Yeah.
So
forget about whether it's exactly solvable.
But then you are defining a different model, which should not be called the Kitaev.
Yeah. Okay.
Okay, so it's an Ising interaction. Yes. You can have Ising interaction, which depends on the bond. So SXSX and the YY, SY. In fact, some people have solved like a bond alternating, 1D, for example. Bond alternating has been done, for example, SX and then minus SX and things like that. I don't know if the 2D with the XX and SY. That's something to think about. Yeah. Yes.
So I wondered about extensions to Kitaev and their possible realization in nature. So as you know, you can extend, there are two things you can do. You can go different lattices, you can go 3 dimensions,
Yes.
the hyper
Yes.
geometric
Yeah.
and things like this. But you can also add orbital degrees of freedom as part of the Yao-Li model.
Mhm.
Has anyone looked into the possibility that you might perhaps have real material with these kinds of interactions in higher dimensions?
So hyperhoneycomb we already have, but in that situation, we know microscopically there are other interactions. Yao-Li's model, is that the with some decorated
Yeah, that's
honeycomb
with,
looking?
That's with Heisenberg and orbital degrees of freedom.
Yeah, I'm
I don't know. I mean, you might imagine that if you had a system with a quartet of states, well, which is the Hilbert space of the Yao-Li model, but conceivably there would be a lattice that might realize such behavior. I don't know.
oh, okay, but it's a quartet, right?
It's a
So
quartet, yeah.
yeah, so that's like you could actually have a quadruples and octuples, which
Yeah,
will.
I'm just curious what
Yeah.
anyone look because they're such fascinating models.
Yeah, I don't know much about that, but if we have a higher spin or quartet, for example, you can in principle have quadruples and octuples, and there are studies, for example, if you have a 5D2, D2 with a strong spin-orbit coupling, you can have a J equal 2, and that J equal 2 will split into doublets and quartet, and that one will have a quadruple and octuples. And then higher order multiplets can also have bond-dependent interactions. So they're also fascinating. And they can be generalized in a material. Of course, it's not a honeycomb there. It's a double perovskite has that, for example.
Right. It seems like very unlikely, but on the other hand, the iridates are also quite a lucky shot. So like just
Yeah.
curious.
Well, you can also think about J effective 3/2 that is sitting up there or down there. So you can think about like a D2 partially filled 3/2 models there and think about, okay, what are the microscopic interactions of the quartet in the 3/2 state? 3/2 is completely, again, spin-orbit entangled. It's made already there for you. So in principle, one can, yes, look into that as well.
Okay, I think it's probably.
Just
Oh, yeah, go
30
ahead.
seconds. So just like these materials you mentioned, sort of,
Mhm.
these level schemes mapped out.
I believe so. So for the case of ruthenium chloride, since 20 something, I don't remember the title, 2014, it has been so many papers that came out, and a lot of details has been known now. So I think energy scales such as spin-orbit coupling and trigonal distortion and interlayer couplings, Hund's couplings, those are reasonably known, as well as the which direction magnetic moment is pointing. And that's also probably.
So they are well separated. You have that double.
Yes, we believe that the half is well separated from the 3/2, at least this one's here. Yeah, this material is actually very old one. This is first slide for the tomorrow. You can go back to the 1892. So it's a very old material, in fact, in terms of, but the details start to show up recently. Yeah, yeah. So I think most of those are pretty well known.
Thanks very much. Okay.